Hey guys, we're going to take a look at our new unit here. We're going to get into what electricity is, and we're going to get to play around with some light bulbs, some circuits. I'm going to give you a simple test to see if you can complete a circuit. Um, so when I think of circuit, what I think of are the word circle. And a circuit is something that makes a complete circle. We look at electric current as the rate of flow of electric charges through space. More specifically, it's defined as the amount of charge that flows past a location in a material per unit time. So I'm going to give you guys a new set of formulas here for electric current. Okay, I will be electric current. Q will be the amount of charge, which we already know from last unit. And then T is per time. So this basically just tells you how much charge runs through a wire or some other conductor per unit time. So current, charge per time. And Q is the amount of charge, as we knew, and then time is the time it takes. So the current depends on the type of material and also the potential difference, which we are going to later learn as what's called voltage. So some materials that we looked at, that we will look at, will be some conductors. And if you've ever noticed a wire, and if you've ever been curious enough to strip the sheathing off a wire, generally you'll find that inside is usually a copper wire. Sometimes it's like stainless steel or something like that, but copper is a very good conductor. It's, the price point of copper is right there, where it's not going to be too costly to run wire, and it does give you a pretty good flow rate. Now, there are other metals that have a better affinity for electric charge. Those would be silver and gold, but that really doesn't make too much sense when you're running electricity and trying to be cost effective. So as we look at electric currents, here's a good analogy, and we can usually do this with electricity. We can make analogies. So a good analogy to help you understand the electric current is to consider water flow. So the flow of water molecules is similar to the flow of electrons, or the charge carriers in a wire. So we know water flow depends on the pressure exerted on the molecules, either by a pump or a height difference, such as water falling off a cliff. So electric current, okay, this I we're talking about, depends on the pressure. So it depends on pressure exerted by the electric potential difference. The greater the potential difference, the greater the electric current. I'm going to get into some of those details shortly. So when we look at current equals charge per unit time, the units can be written as amperage. Okay, 1 amp is equivalent to 1 coulomb per 1 second. This is often referred to as amperage. And when we start looking at circuits, I'll write it out here. Okay, we can start drawing diagrams of what a circuit might look like. So an electric circuit's an external path that charges follow between two terminals using some sort of conducting material. For charge to flow, the path must be complete and unbroken. So, for example, a conductor might be copper wire. So, and you can think of it as copper wire as a pipe which holds electric charge. So, when we draw a battery symbol, okay, I'll kind of draw like this. Okay, positive. I'll call this negative. So here's the part that can be a bit confusing to people. I'm going to draw the picture here. Okay, so we call this direction from the positive to the negative. We call that conventional. Current. Okay, current flow. Okay, the actual electron flow goes the other way. So the electrons actually flow this way. But in common practices, if you ever get into electrician work or anything like that, common current flow is said to go from positive to negative. Okay, so from the big side to the small side. Okay, and there's the big side of the battery. There's the small side of the battery. Now, so we're going to look at a conventional current flow, but we know that in physics that electrons are doing the flowing. So conventional current flow gives you a situation where we're going and a current that's flowing this way. This is a switch. Okay, and it comes through, and we might have some sort of resistor here. Okay, this could be a light bulb. Okay, and then it goes back into the negative side of the battery source or power source. So it's like a current. It's almost like a tube. If I break the tube here, the current stops. Okay, it doesn't make it through. So that break in that switch will shut that light bulb off. Okay, this is a very simple circuit. And we mentioned there was a power source here. Now this could either be a battery or a power source that's plugged into the wall. So we have, you guys have been pretty familiar with batteries. Usually there's like a battery like that. That might be a C or a D battery. Usually the part that comes out here is the positive terminal, and the part that's on the bottom is the negative terminal. So positive, negative. So we can use a battery, the chemicals inside. We can convert the chemicals to create electrical energy. So basically the chemicals act like an escalator carrying the charge to a higher voltage. So generally a battery is about 1.5 volts. And we'll talk about what voltage is a little bit later. And then we can make a connection. So this battery here, here's a positive. Okay, we can say that we can connect something to that side, switch it, and put our light bulb here. And then as long as we make a connection here, okay, if we close that switch, then the flow of electrons, we know flows this way, but our current convention says it goes this way. We will light the light bulb. All right, so this can be achieved a couple different ways. We can get a power generator, a power source, or stick a battery here.